Alright, this is lesson 4.2 on irrational numbers. In the previous section, what we explored was a math lab where we learned about estimating roots. And in this section, we're going to talk about a different set of numbers that you probably haven't experienced a whole lot about, and that's irrational numbers. Alright, so let's get started with this. The formulas for area and circumference of a circle, of course, involve pi, one of my favorite numbers, which we would say is not a rational number. Not a rational number because non-rational numbers cannot be written as a quotient of integers. So for instance, you could never take, I know a lot of people think pi is 3.14. You couldn't take, for instance, 6.28 and divide it by 2 and just say that we have pi. So what we'll say for this is basically if you can ever write a number as a fraction where m and n are both integers, then therefore we have a rational number. Alright, so that's what we're going to be exploring in this section. So the first little activity I have is something I'd like you to do with a partner. So try and find someone that's around the same spot with you and see if you can complete this activity. So it's just on this front page where it says A, B, C, and D. Alright, so what I'll do now is I'll go through how you would have done this activity so that you can check your answers, or you just may want to fast forward to the end where I have the answers down here at the bottom of A, B, C, and D. Okay. So the first part of this, what we have is we have examples of what are rational numbers on the left-hand side right here, and we have examples of numbers that are not rational numbers. And you'll notice something that's a little bit different between them. So let's start with the left-hand side here. You notice that the square root of 100 is a perfect square. What I mean by that is we can take the square root of 100 and it gives you a whole number. It's equal to 10. All right. 5 over 6, that's already written as a fraction. All right. So all of these numbers in here can be simplified so you can write them as a fraction. As an example, I'll do a couple more. 1/2 can be written as, well, of course, 1/2. The fifth root of negative 32, that's the same thing. You might need to use your calculator for that, but what that's saying when they say the fifth root of negative 32, what number do you multiply by itself 5 times such that you get negative 32? And that, of course, is negative 2. All right. All of these numbers, even the first one I started out with, positive 10 up here, it can be written as a fraction. For instance, 100, when I take the square root, I got 10, so I could write that fraction as 20 over 2. All right. These are all examples of rational numbers. They can be written as a quotient, as a fraction. On the other side here, if I was to take any one of these 5 examples and put them into my calculator, you'll see that you're going to get a number that I always consider kind of ugly. As an example, if I take the square root of 0.24 and I put it into my calculator, you're going to get a decimal that goes on forever and does not really have a pattern. It may look like it has a pattern, but those numbers are always going to be different. As an example, I'll take another one. How about the square root of 2? Same thing's going to happen. Okay, you get this crazy ugly number. Whereas if I had done that with any of the examples on the left-hand side, you would have gotten a decimal that would have terminated or would have repeated consistently. So, A, it says, how are radicals that are rational numbers different from radicals that are not rational numbers? Well, we basically just talked about that. So my answer for A here is going to be simply that they can be written as a ratio or as a fraction. Okay, all those ones on the left-hand side up here. Let's take a look at B. B says, which of these radicals are rational numbers? Which are not rational numbers, and how do you know? Well, let's just answer, we'll just kind of ignore this part. Let's answer the top part, because if something is irrational, then we can assume that the other ones are not. So rational means, can we write them in terms of a fraction? Can they be simplified? A couple easy ways of doing this is you can stick them into your calculator and see how they look. For instance, if I take the square root of 1.44, all right, you get 1.2. Since that fraction, or since that decimal terminates like that, you know it's going to be a rational number. We can write that as a fraction. As an example, that would be 12 over 10. All right, so we would say that the square root of 1.44 is a rational number. All right, the next one. Alright, whenever you have a fraction inside a radical like this and you can take the square root of both numbers, then that one's going to work. So I'll write that one down here. What I mean by that is, imagine if you take the square root of 64, we would get 8. And the square root of 81, we would get 9. Alright, if I was to go and put this into my calculator now, you'll see that I'll get that as a fraction. I get the square root of 64 divided by 81. It's going to give me this repeating decimal, but if I use that math fraction button on my calculator to see what that is as a fraction in lowest terms, you get 8 over 9. The next one, rolling right through here. The cube root of negative 27 is saying, what number do you multiply by itself 3 times such that you get negative 27? Well, it turns out it's negative 3. So we could say that that is also a rational number. Okay. Now we start to get in some problems right here. Yeah, you can take the square root of 4, but you can't take the square root of 5. 5 is not a perfect square number. Whenever that's going to happen, you know that it is not rational. Same with the next one. So those two would fall into the category of not being rational. So maybe I'll just highlight them up here so that you guys know that they're somewhat different. All right, C says, write 3 other radicals that are rational numbers. Why are they rational? So let's look for those radicals. I'll try to give you guys some interesting ones. Let's deal with the square root of 0. Now, square root of 0 is saying, what number do you multiply by itself such that you get 0? Well, that is just 0. And could you write 0 as a fraction? Sure, because if you put 0 over anything, let's say 2, it's just equal to 0. So that'd be an example of 1. Let's deal with a cube root this time. Now remember what cube roots mean. They mean what number do you multiply by itself 3 times such that you get that number? Well, the cube root of 8 we know is 2. 2, you can write that as a fraction, 4 over 2. There we go. You're going to see that sometimes we can have decimals. And the decimals, what you'll notice, anytime you see a perfect square number, what do I mean by that is we should know that 225 is the same thing as 15 squared. So when you have 2.25, you can probably assume that that's going to be 1.5. And we know that 1.5 can be written as a fraction 3 over 2. Just to confirm this with you, I'll show you how you can check this into your calculator and see that indeed we did get that as a solution. Okay. So why are they rational? Well, basically we just talked about that. We can put them as a fraction. So D says, write 3 other radicals that are not rational numbers. Why are they not rational? Well, I would take numbers that are not perfect squares, that are not perfect cubes, and so on. So for instance, we know that the square root of 4 is a perfect square, so it means you could take the square root of 3, for instance. If you put that into your calculator, it's not going to be very nicely. Not going to work out very nicely. Let's take a cube root one. Well, if I know the cube root of 8 works out, then the cube root of 9, believe it or not, isn't. Because what that's saying is, what number can you multiply by itself 3 times such that you get 9? Well, I'll show you on your calculator here. For me, the cube root's hidden in, it's hidden in the math function here, under the 4th one. So if I take the cube root of 9, it's saying that if you take this 2.08 this number that goes on forever, and multiply by itself 3 times, you will get 9. But since that number goes on forever and does not have a pattern, it is irrational. Lastly, I don't know, let's pick one more. We could have the square root of 101. All right, we knew the square root of 100 was a perfect square. Square root of 101, then therefore cannot be. All right, next page. Notes. Radicals that are square roots of perfect squares, cube roots, and perfect cubes, and so on, are what we consider rational numbers. Rational numbers have decimal representations that either terminate or repeat. Okay. So, as an example, some people, when they see, let's say, 2/3 written out as a decimal, to look like this, it goes 0.666 and just keeps on going, right? Well, they'll sometimes think, oh, that's irrational because it's repeating and it just keeps going. No, that's not the case. Since there's a pattern, then we can say that that is rational. All right. So here's the definition for an irrational number. Okay, straight out of the textbook here. An irrational number cannot be written in the form m over n. Basically, that just means it can't be written as a fraction, where m and n are integers such that n cannot equal 0. The reason I have this is because, of course, we cannot divide by 0. If that happens, your page explodes. The decimal representations of an irrational number neither terminate nor repeat. Okay, so continuing on. When an irrational number is written as a radical, the radical is the exact value of the irrational number. We can use the square root and cube root keys on a calculator to determine approximate values of the irrational numbers. There are other irrational numbers besides radicals. So for example, one that we talked about when we first dove into this lesson was pi, our good friend pi. Well, we can approximate the location of an irrational number on a number line. If we do not have a calculator, for instance, we can use perfect powers to estimate the value. All right. So, for example, to locate the cube root of -50 on a number line, well, what you have to look for, and this might remind you of what you did in grade 8, but now we're just kind of kicking it up a notch because we might be dealing with, I don't know, perfect cubes here to the 4th power, those type of things. So it's getting a little bit more crazy on us. So, for instance, to locate the cube root of -50 on a number line, we know that this is a perfect cube. The cube root of -27 gives you -3. And we know that the cube root of -64 gives you -4. So since we see that root, the cube root of -50 is between there, we can make a couple guesses right here. All right, so here are a couple guesses that I went and gave a try. The cube root of -50, I thought, well, since it's between -3 and -4, let's start with somewhere in the middle. So it looked to me like it was going to be slightly closer to the -64. 50 is obviously closer to 64 than the 27. So I started with -3.6, so that's this one right here. So what it is, I went and tested it, I put it into my calculator, and I took a look and I found, yeah, it's getting there. It's close to 50, but not quite 50. The next one I did was I took a look at -3.7. And so that's the next one. I thought, well, I'll try one a little bit higher. And this one I got fairly close. So this is just one way that you can go ahead and estimate these. And so on a number line, what I would have done is something like this. If I said -4 is right here, and let's say -3 is at the end here, well, if this is -3.9, -3.8, -3.7, this one would be slightly less than -3.7. So I would say that the cube root of -50 lives somewhere there on a number line. All right, so that's how we can go about estimating those. Let's go to the last page. Relatively quick little lesson right here. Your assignment is just going to be you guys playing around with identifying what is and what is not rational numbers. So we play the irrational or irrational game right here. Yay or nay, what are we dealing with? Well, let's take a look. So this one. You might notice that 49 and 16, they kind of stick out like a sore thumb. Since they, when you take the square root of them, are both rational, then we can say that the square root of 49 over 16 is. All right. So in the years to come, what we'll be doing is we'll be simplifying these. So what we can say is that rational, this is rational, since we know that the square root of 49 equals 7, and we know that the square root of 16 equals 4, then therefore this is just the fraction 7 over 4. All right, beautiful. Now let's take the next one. Well, this one's saying the cube root of -30. Well, cube roots are what number can you multiply by itself 3 times such that you get that number? Well, if you need to, folks, and we'll be going over this in this section, your perfect cubes go like this. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64, and 5 cubed is 125. Those are the ones I need to know. Now, incidentally, if I put a negative in front of all those, it turns out that, like, if I made this -3 cubed, you'll get -27 over here. Well, since -30 does not fall into that list, we can say that it is irrational. Since -30 is not a perfect cube. Number. Okay. Now the next one. We have 1.21, just simply any decimal. Any decimal that terminates, I'll just let you know right away, it's going to be a rational number, and here's why. It's rational since it can be written as a ratio. As an example, if you recall, any number right now you could say is written over 1. Now we can't technically have decimals in fractions, but if you look, if I move the decimal place over a couple times, I have 121 over 100, and if you put that into your calculator, you would see that that's equal to 1.21. Alrighty, last thing I got for you. What I want to do is I want to talk to you guys about how you can classify numbers. So together it says the rational numbers and irrational numbers form the set of real numbers. Alright, so in this diagram what we're going to be doing is we're going to be looking at numbers and seeing how different numbers belong to different sets. So we're going to work our way from the inside out. The first set kind of in here we have is natural